Today, I would like to introduce the system modes approach that we developed within the MicroROSE project. It is a concept that provides appropriate abstractions for system configuration, effectively easing reconfiguration of entire robotic systems at runtime. The system mode concept is motivated by the observation that the deliberation layer of a robotic system, the one that orchestrates the system and its skills on a mission level, is often tightly coupled with the skill level, effectively preventing decoupling of these two layers. We observed that the deliberation layer interacts with the skills of a robotic system mainly for three aspects. First, the intended task, that is the happy path, so to speak, where everything works according to the plan. Second, contingency handling, that is expectable exceptions, like for example, obstacles blocking the way or retrying a failing grasp in a manipulation task. And third, system level errors that should not occur, that is, for example, sensor failures or software components crashing. While common robotics frameworks and middlewares provide good abstractions for parts of this communication, namely publish, subscribe, actions, and services, allowing effective decoupling for these aspects, some other aspects are often not well abstracted. According to our observation, this is, for example, the runtime lifecycle of components, diagnostics, as well as parameterization. For these aspects, the deliberation layer often still needs to be aware of the actual implementation of the skill, which prevents decoupling. System modes now try to fill exactly this gap by providing appropriate abstractions for these aspects as well. Now, how do we do this? Our system modes concept assumes that the software of a robotic system is built of components with a runtime lifecycle. These components implement the skills of a system. In ROS, these components would be termed nodes, for example. You can see a typical runtime lifecycle on the right side. It can be activated, deactivated, and shut down, and may be in an error state. Now, the system modes introduce a few more things on top of this assumption. First, we introduce the concept of modes. These modes extend the active state, as you can see on the right side, and are defined by a set of parameter values for a node. For the sake of this presentation, I will show you these modes and the further concepts we introduce in a concrete example, how we would specify these in a model. So in our model file, you would first start by defining which nodes your system consists of, which modes these nodes have, and what the parameter values are for this mode. As an example, consider a drive-based node that has a default mode and a fast mode. In the default mode, the maximum speed parameter of this node would be set to 0.1 meter per second, and in the fast mode, this would be set to 0.3, for example. Now, as a second concept, we introduce systems. That is a logical grouping of nodes and other systems. So think system of systems. We also introduced that these systems have the same life cycle as the nodes. So they can also be activated, deactivated, and shut down, for example. So in our model file, this would like this. You specify a system, give it a name, and specify its parts. That can be nodes or other systems. Consider an actuation subsystem, for example, that consists of the drive-based node that we specified above, as well as a manipulator node that we would also specify within this model. Last but not least, we introduce modes for systems. Now, these look a bit different from the modes that we introduced for nodes, as they now don't specify parameter values, but instead specify how the state and mode of their system parts look like. Consider again the example of the actuation subsystem that might have a default mode and a performance mode. In the default mode, the drive base would be active and the manipulator node would be inactive. In the performance mode, the drive base node would be in its fast mode that we specified above, and the manipulator is active. The main part of the system modes concept is the mode inference. That is, we can, based on this model, infer the system modes bottom up, as illustrated on the right side. Blue boxes indicate nodes, so actually running software entities of your system. Gray boxes indicate the inferred system modes model that is maintained at runtime. So as we can directly observe the current state and parameterization of the nodes, that is possible in common robotics frameworks, we can infer the current modes of the nodes according to the mode specified in our model. And if we know the states and inferred modes of the nodes, we can then infer the states and modes of the systems as well, according to the mode specified in our model. This way, we can infer all states and system modes of the entire system. In the implementation of this concept, we provide a so-called mode monitor that provides a live view of the currently inferred states and system modes of the entire system. This is, of course, the same information that is available to the deliberation layer, which now no longer needs to know the implementation details of the skill layer, the nodes, but can instead rely on the inferred knowledge of the overall system state and mode. Again, providing an easy abstraction for the deliberation layer to observe the state and mode of a system at runtime without the necessity to know the implementation details of the skill layer. Now, while we do this inference bottom up, we also allow to request a certain configuration or reconfiguration of the entire system top down by applying a certain system mode. This is done by the so-called mode manager that allows management of all states and modes of the system. If a certain mode is requested for a node, the mode manager will set the parameters according to the mode definition in the model. If a mode change is requested for an entire system, the states and modes of all its parts will be changed accordingly top down. While we developed the system modes concept in the MicroROS project, we want to report on an additional evaluation that we performed within the ROB-MOSES project MROS. MROS is short for Meta Control for ROS and is a concept developed in a different project that we wanted to integrate with system modes. Meta Control implements runtime adaptation of robotic systems based on ontological reasoning. Ontologies in Meta Control mainly comprise functions that would be, for example, navigate to a certain goal, follow a path, grasping, and so on. And they comprise function realizations, that is, configurations of a robot system that is capable of performing these functions. These function realizations include specifications of quality attributes and the required resources. As an example, you could have different function realizations for the navigation function, which use different sensor sets and with them provide a different quality of service. So, for example, different precision of the navigation. Now, the catch is that these function realizations have a very good mapping to the system modes, since system modes also provide a good abstraction of a system configuration and its required parts. We evaluated the integration of Meta Control and the system modes in a mobile robot navigation use case. To demonstrate this, in the following video, you will see how the Tiago robot starts navigating through an office. Then, a laser failure is artificially introduced, rendering the current navigation function realization impossible. The Meta Control system will then reason about this, select a different function realization that doesn't rely on the laser, and the mode manager will be instructed to apply an according system mode, effectively changing the robot configuration to one that can fulfill the navigation task, but without the laser. To sum up, we presented the system modes concept that is intended to allow further decoupling of the deliberation layer and skill layer of a robotic system by introducing abstractions for configuration and reconfiguration of robotic systems. The concept was developed and evaluated in the publicly funded MicroROS project and evaluated in 2 further use cases in the ROB-MOSES project MROS. The concept is available open source as an C++ implementation for ROS2, released for all 3 recent ROS2 distributions. The two links below give you access to the code to reproduce the experiment shown in the video in simulation.